Um, so yeah, also today, I might have mentioned last week that I was planning on starting chapter 10 after we finish the new stuff, but I think just, based on my experience with sequences and series and how people deal with it, I think we need a review. So the bulk of today is going to be review. I have one last thing we need to talk about that's brand new. That'll probably take us 40 minutes or less. From there, you do have a quiz about this stuff, which I will post later tonight. It is not due until Thursday at 5. So I know I extended the homework out one more day. If you've been working on that, then that's good. You definitely have a good idea of what things you need to review and what things you need to get polished up before tomorrow evening. And hopefully after tonight, if you have gaps in the homework, you can definitely finish it off. I think I also said at the start of the class this summer that there'd be 6 homework assignments. The next one's going to be the last one. I think that's about all to go over. Any questions about the things that are going to happen between now and the day the class ends on the 24th? Yeah, the 24th. Okay, so let's go ahead and get started on our last section here. So last Thursday we talked a lot about Taylor series and basically how they are used to represent any function. No matter what the function looks like, you can use this Taylor expansion to represent it as an infinite polynomial series. Today we're going to learn basically how to figure out how good those approximations are. So we know that this is just a generic Taylor series representation of a function, and hopefully this looks familiar to you from last time. Basically, this is, you're just using I don't want to say series, but you're using basically a list of derivatives to figure out what these coefficients are. So basically you're taking an infinite number of derivatives of whatever function you are worried about to find all these coefficients that are in front of basically your variable term. So this series is infinite. The problem with that is, and I think those of you who are here on Thursday or watched the video saw, I tried to graph using a software package. I tried to graph, I think it was 50 terms of a Taylor series, and I had to give up on it. It was taking too long. So in theory, infinite Taylor series are great. We don't have the technology. We're limited by time, computing power, all that stuff. We can't use infinite Taylor series. So we can't use it practically, so we need to create a Taylor polynomial. And really, the only difference between a Taylor polynomial and a Taylor series is I'm going to shorten one. Basically, I'm going to say, all right, I only want the first 5 derivatives. I only want this to be a degree 5 Taylor polynomial. But the problem is when you do that, you're opening yourself up to error. And in most real world cases, you're going to see that, yeah, you have to accept error because there's no way to perfectly zero in on something. So we have to decide how much error is acceptable. So we're going to use this this idea called Taylor's inequality, and we could derive it. I don't think it's terribly value added, but I'll try to point out some things on kind of where certain things come from. But I will be giving this to you. So if you remember from our first test, we had on the front page I gave you all or not all, but enough of the trig identities, basically all the ones you needed. This is the only thing I'm going to be giving you. Everything else should be, think about what we've done in the last couple of chapters. most of the things we've done basically, you know, are definitions and, you know, tests you have to apply, but you really have to know how to apply those tests. This is the only like quote unquote formula that you're going to be responsible for. So let's go ahead and just unpack what a lot of these things mean. Hopefully some of these are going to be familiar to you, but we're definitely introducing a couple of things. Basically this this term R and this term M. It's one of those. So this R sub N, basically that is the largest possible, I left out a word here, but really the largest possible error under whatever circumstance, or yeah, under whatever conditions I give you. So really there's some things I have to specify. The most important one of those is really this value N. Basically that N is how many terms in this Taylor series am I going to take? Because you can't take them all. So I want, do I want to go up to the 4th power of X, 10th power of X, 20th, whatever? That's what the N represents. Oh, is there anything else we need to unpack here? M is, I kind of glossed over this, but M comes from this idea here. Basically, whatever degree of Taylor series I want, this inequality, basically this term M comes from 1 degree beyond that. So for example, if I'm trying to generate a 4th degree Taylor polynomial, then this error is going to be given by my 5th derivative, the next one up. Any questions on this before we do an example or two? And right now, I'm sure it looks pretty mysterious, and hopefully it will look less mysterious after we run through this a couple times. All right, so I want to use a 2nd degree Taylor polynomial to represent the cube root of X in this neighborhood. So basically, I want to center around X equals 8. And so remember, when you do a Taylor series, wherever you're centering your Taylor series, everything is going to be accurate there. The value of the function, every derivative, they're all going to be perfect at X equals 8. But if I, Taylor polynomial, these approximations aren't really useful unless I deviate from that center value a little bit. So I want to know specifically if I'm 1 unit on either side of 8, I want to know basically how good is this approximation going to be. So I want N to equal 2, if I'm keeping this kind of in the language of that formula, I want N to equal 2 and I want A to equal 8. So I'm going to go ahead and rewrite my function. So this is going to be X to the 3rd. So see if I can remember this. Basically, I want R of 2. Basically, I want to know what the possible error is for a 2nd degree Taylor polynomial. And so I'm looking for you're seeing this is not an equal sign because I'm looking, basically this error bound I'm looking for is a maximum. There are going to be several places where the accuracy is better. So I need to look for the worst case scenario. So I'm looking for M over N plus 1 factorial times X minus A, absolute value of X minus A to the power of, I believe it's N plus 1, but yeah, it's N plus 1. And we need that, but really where does M come from? M is equal to the absolute value of the So there's just reminding you of the setup that I showed you on the previous slide. Any questions so far? So based on what we have here, what do I need to do with this function? So I need derivatives, but how many do I need?
We need two.
Definitely need two. So first derivative be 1/3 x to the negative 2/3. Second would be -2/9 times x to the negative 5/3. All right, so I got my two derivatives. So for this Taylor's inequality here, I need really to evaluate this. I need to figure out what this value for n is. But the interesting thing about, the reason Taylor's polynomial is so useful is, I could. So let's just keep it grounded in this example here. I want a second degree Taylor polynomial, so quadratic. I could very easily come up with another quadratic that could approximate this. That wouldn't be that hard. What makes this Taylor inequality special is that I'm getting my error from the next derivative for something of a higher order. And because of that, so I'm going to use a second degree Taylor polynomial, but because I need that next derivative to help me bound, or help me figure out what this constant n is, I actually need to go one derivative beyond that. So I need my third derivative as well. So 10/27 x to the negative 8/3. And now I'll go ahead and rewrite all these, or I guess I'll just rewrite the last one. This will be 10/27 times x to the 8/3. So this is where my m is going to come from. So I'll go ahead and put some specifics behind that. M is going to be less than or equal to 10/27x to the 8/3 over n plus 1 factorial. So that's going to be 3 factorial. So 10/27 times 6. I would encourage someone to check me on this, but I think this is the right number. 5/81 times x to the 8/3. So remember, I'm looking for the worst case scenario here, so I need to maximize this number. And I am looking at this interval with x values between 7 and 9. What x value on that interval is going to give me the highest value of this term right here? So look at where the variable is. The variable only shows up one place there. And if I want to make this whole thing as large as possible, what do I need to put in for x? Something large or something small?
Something small.
Something small, right? So the smaller the denominator is, the larger this value is going to be. So n is going to be equal to 5/81 times 7 to the 8/3. not something I can do in my head. If anybody gets to the end of this book, gets this number before I do, please let me know.
I got 3.44 times 10 to the negative 4.
Okay, sounds good. Thank you. All right, so I got that as my value for m, and from here it's just basically got to run this through one more calculation, and then we have the maximum error. So I'm trying to find this r stands for remainder essentially. So basically, how far off of the real value am I going to be using this? So I got this value for m, so that's 3.44 times 10 to the negative 4 times x minus a. So remember our x value we care about, basically the one that gives us our m. We said that was 7 minus 8 to the n plus 1, which is going to be 3 all over 3 factorial. So 3.44 times 10 to the negative 4 times 1 all over 6. So for that, I am getting 5.733 times 10 to the negative 5th. Any questions on this one? All right. Let's go ahead and do one more. So this time I'm giving you the Taylor polynomial. What degree Taylor polynomial is this?
Five.
So yeah, remember, so I just wanted to, the reason I'm asking is because remember, we're looking at not number of terms, but highest power on x. So this is our polynomial. We're looking at it over the interval from -3 to 0.3. And we want to approximate sine of 12 degrees. So where do we need to go from here?
Define, do an integral. No.
No, so I've given you the Taylor polynomial, so we don't need to yeah, we don't need to do any derivatives or antiderivatives. We've already, basically, the reason I took all these derivatives in the last example was to basically get the terms in this Taylor polynomial. So I'm actually, basically, I'm ahead of the game on this one. I have the Taylor polynomial. One thing we need to do is, you know, it might not seem like 12 degrees is inside this interval, but this interval above is represented in radians, and I'm trying to approximate something in degrees. So I need to, first thing I need to do is to convert 12 degrees to radians. So hopefully this thing looks familiar. I believe that's pi over 15. Which we're going to approximate this whole thing anyway, so let's go ahead and just approximate pi over 15. Uh, 0.20944. All right, so another thing we need to pick up from our Taylor polynomial is this. What is our center value for this Taylor polynomial?
Would it be 0?
Yeah, it's just 0. Because remember this, basically, you mean what you have in this in Taylor polynomial, and it's more obvious when we have a center value that's not 0, but remember these are always going to be x minus a. I'll just write it in terms of this one, x minus a cubed over 6 plus x minus a to the 5th over 120. So if you kind of compare these, you know, we're not offsetting by any a value, so it's just basically x minus 0. So we know the center value. We know basically we know the value we're interested in. So now we can find this maximum error. So remembering back to our last example, what's my next step in figuring out what this maximum error is?
Set up R5.
Okay. Yep, so we want R5. That'll be less than or equal to m times x to the 5th, actually not 5th, x to the 6th over 6 factorial. All right, so that's a good setup when we're ready for it, but remember we also need to find m. So we got m, which is less than, or really it's, so it should be like, should not use less than, should use equal to. And really we are looking for f the 6th derivative of f of x over 6 factorial. So other thing we need to look at is what's the function that this Taylor series is representing?
X raised to 2n plus 1.
Sorry, what was that, Reese?
X raised to 2n plus 1 by...
No, so what I'm asking basically is, so you have a Taylor series here that is basically this polynomial represents basically it is the approximation of some other function. And since we are trying to approximate sine of 12, then that kind of tells me that the function I'm representing here is sine of x. And in fact, if you look at your notes or basically my slides on, in the unit where we first introduced Taylor series, you'll see that, yeah, sine of x expands like this. So really, to find out this m here, we need the sixth derivative. And I'll take a couple derivatives and I'll skip ahead, but first derivative will be cosine x. The second derivative will be negative sine of x. And if you remember how these derivatives cycle, I can also say that the sixth derivative is negative sine of x. If you're not convinced of that, basically you can take a couple more derivatives on your own to see that these just repeat every 4 derivatives. So basically we have negative sine of x. And I care about the interval from negative 0.3 radians to 0.3 radians. I know that when sine of 0 is 0. And I also know that the sine function is symmetric. So really, it does not matter which of those endpoints I use. So I'll just take sine of. Basically, I want to find f double prime, or sorry, negative sine of 0.3. And if I divide that by 6, this comes out to be 0.04925. And then from here, I can calculate my remainder. And I took this at 0.3. I need to raise that to the power of 6. And then I need to divide that by 6 factorial, which is, correct me if I'm wrong, but I believe it's 720. So hopefully that makes it clear this error is going to be incredibly small. And someone please double check me on this, but here's what I'm getting. So if someone wants to give me a sanity check on that one, I think this is my value of R.
Isn't that ultra tiny?
That's very small. I mean, it's much smaller than one we had in the last example. I think by forward, or I think the last one was on the order of 10 to the negative 5th. So this one is, basically in the neighborhood of 1,000th of our previous number. And that really comes from the fact that, I mean, this is a 5th degree polynomial. The one we just looked at was a 2nd degree. So remember, a Taylor polynomial only gets more accurate with more terms.
I'm
All right.
confused with the sine 12.
Sine 12. Yeah, so we haven't used that yet.
Oh, okay.
Kind of jumped the gun on converting that, but really the first bullet there is just to find the maximum error. So that means, look at where sine or 12 degrees falls. That's definitely inside our interval. So our error should be, less than this very small number that I came up with. So if I use my polynomial to approximate this, what do I get? 0.20944. 20944 cubed over 6. And while I'm writing this down, if somebody can help me out with the actual crunching of the numbers, that'd be great. All right, I believe this is 0.207912. So let's also find, let's just do it using just the sine function. And unfortunately, my calculator, actually, let me get some more decimal places because I'm to 6 decimal places. They're exactly the same, which should be expected because our error, you need at least 8 decimal places. So I'm going to go ahead and open up my document settings. Let's do 12 digits. So the actual sign to 12 digits is this 0.209207912. 169.876. And this other calculation I did, 0.207912. 169.876. So I cannot take my calculator out any more accurate than the 12 decimal places, but obviously this approximation is very good. So we have our maximum error, which really only happens at the endpoints, and yeah, inside the interval, the approximation is going to be even better. Which here, our error is less than 1.0 times 10 to the negative 12. Any questions on how this works? So like I said,
why did you take R5? That's just like I'm still a little bit hung up on that. The R5.
Yeah, so like why is it called that? What do you mean?
Yeah, why do you, I mean, I understand how you found the errors and stuff, but then the R5
Yeah, so that capital R stands for remainder, and basically that remainder is, so under these conditions. So what are the conditions we're worried about here? One of those conditions is, I'll just go ahead and title this, what the heck? So a few things that matter here. One of those things is, what is my degree? How many, what's my highest order derivative that I took to make this Taylor series? And for me, it's 5. For this one, it's 5. What else is am I worried about? The other one, another word I'm worried about is what's the center value? In this case, a is equal to 0. What else am I worried about? And I'll just call this I for interval, negative 0.3 to 0.3. So, because if you look at basically what R relies on is those three things. So what's the degree? Where am I centered? And basically how wide is the interval? So in fact, so remember that this derivative here, this highest value came from, really it could have come from either endpoint of the interval. I just chose the positive one because I had to pick one. But really, if I open this interval wider, then I'm going to have more error. If I decrease n, like maybe let's say I don't go up to the fifth derivative, then the result is I'm going to have to deal with, instead of dividing by 6 factorial, which in this case is 720, I'd be dividing by 3 factorial, which is 6. So that is a hugely significant change there. So the higher the degree, the better the approximation. The wider the interval, the worse the approximation. And hopefully that becomes clear from, so I am guaranteed an error of no larger than 4. Basically, let's just call it 5 times 10 to the negative 8. But when I'm inside that interval, like basically closer to 0, my error is I couldn't even detect an error because I can't even look at enough digits. What else to mention? And this a equals 0. So that's important, but there's no rule of thumb there. Like it, maybe changing it would make the approximation better or worse. It totally depends on the function. Anything else about this approximation method using Taylor's inequality? Okay, so that really is a wrap on chapter 11. So go ahead and close this down. The next thing I'm going to go over, basically, like I said, I think just based on where we are and how demanding these concepts are, basically I want to spend the rest of this time reviewing. So, and basically I'm going to largely take my hands off the wheel here. I mean, this review is for you. You have seen all this stuff before. It's been in homework assignments. It's been on quizzes. Pretty much all of it. I mean, with the exception of the stuff that I just went over, you've seen it before. So, and like I understand. I mean, a 6-week class is calculus 2 in 6 weeks is daunting, and it moves pretty fast. But really, this review is for you. I'm gonna totally take my hands off the wheel. So I'll kind of take all my inputs from you. The last thing I want to say about chapter 11 before I go into these review slides here is that the web work set for section 11 is not due tomorrow, but it is going to be on the test. So I really recommend you at least look at it, and if nothing else, figure out what you're bumping your head against and bring those questions tomorrow. All right, let's go ahead and get into this. So this is going to be more or less chronological. Let's go straight back to the beginning. So chapter 8 started out with arc length. So I want to find the length of this curve between these 2 points. So what's a good place to start?
Quick question. Where are these slides?
Or these, oh, am I not sharing them?
Oh, no, I meant like, because I usually print them out. Is that possible?
They are not on Canvas yet, but you know what? When we take a break, I'll put them on there. But yeah,
Alright,
I just got done making this a little while ago. But yeah, I'll make them available to everybody. You know, when we take our our mid-evening break.
Derivative.
Okay. Take a derivative. That's going to be a little difficult with this thing.
Definitely doable.
It's doable, but I think there's probably a simpler way to go. So something we can do before the derivative that would simplify things.
You could derive it with respect to dy.
Right. Okay. So you want to set up a dy integral, which means we're solving for what variable?
solve for x.
X.
Solve for x. So first thing I'm going to do here is I'm going to divide both sides by 24y. And from there, we're going to get x equals, I'll just call it f of y, equals y cubed over 24 plus 2 over y. All right, good so far? All right, that's good. I believe someone said take a derivative a bit ago, so let's go ahead and find f prime of y, which kind of weird to see it written this way, but this is going to be dx dy. I'm taking the derivative of x with respect to y. So that'll be 3y squared over 24. Let's do this here. Y cubed over 24 plus 2y to the negative 1. So this is going to be minus 2y to the negative 2. So simplifying a bit, we got y squared over 8 minus 2 over y squared.
Cross multiplying it and take inverse.
Cross multiply.
Like you can do y squared, y raised to 4 minus 16 by 8y squared. And then dy by
Oh,
dt.
okay. Yeah, so you're adding these together. So common denominator of 8y squared. So that becomes y to the 4th minus 16. All right. So that's good. All right, what now?
You can take it. Is there any problem like taking instead of like taking dy by dx, like instead you just take dx by dy?
No, you can absolutely do that. That's what we just did.
I mean, yeah. So can I just substitute dx by dy into that for a formulation, that square root of that one?
Okay, so let's fill in some details here. We're not doing s of x, I'm doing s of y. So what's this integral going to look like based on where we've started?
Integral a to b
A to b.
square root of 1 plus f dash of x. F dash
Not
of
of
x the
x.
whole square.
Yeah, not of x, but of
Oh yeah, y.
Yep.
Dy.
dy. Good. All right, so we have f prime of y squared. Or we haven't squared it yet. In fact, what I would like to do, unless really, if anybody wants to go through it, we can, but I had intended only to set up this integral because I think, as we know, that's the more important part. So let's at least set it up and then we'll see how we feel from there. This is not going to be a function. It's going to be a number. What are my endpoints? What are my limits of integration?
Wouldn't it be 2 and 4?
How'd you know that?
Because we're using y values.
Yeah, absolutely. So yeah, yeah, you're integrating over a y interval, and then we have 1 plus. Does anything convenient happen when I square this? Get y to the 4th over 64. Minus a half. Plus 4 over y to the 4th. dy. So let's go ahead and simplify that before we make our decision. Y to the 4th over 64 plus 4 over y to the 4th plus a half dy. All right. So from here, this will take quite a bit of time to actually evaluate this. And I believe that time is better spent, reviewing as much as we can. Does anybody have any objections if I call it good here? Yeah, I got one no. So, any questions about how we put this together, how we set this up? All right, very good. Let's go ahead and move on. Surface area. So I have a parabola. I would like to rotate it around the y-axis. So what do we want to do?
Two pi r, 2 pi s.
2 pi r. Okay, so
Uh,
2 pi r, 2 pi s is what you said?
I think it's 2.
So this is one good reason, why to at least draw a sketch. So let's go ahead and do that. So I am only going from 1, 0 to 0, 1. So here's a parabola. I am going to revolve this around, can I get another color? I don't know how to do that on PowerPoint. That's okay. So let's say I have an interval like this. So I want to take a little strip here, revolve this around the y-axis. So I guess one thing I did that is really a choice you can make, but by me making this interval here, basically what do I have to do? Like, what does my integral what has to be true about it? Based on the fact that I drew a vertical interval like this.
It'd be dx.
Yeah, so and really, sometimes it's better to do that. Sometimes it's easier to do it in terms of y. I think this case is probably equally complex doing it either way. But yeah, we're going to set up an integral with respect to x. So where do we go from here?
Oh, 2 pi x dx.
2 pi x dx.
ds or
ds. Good. So before we go too much further, how did you know to do that?
intuition.
Intuition?
I
Okay.
mean, like, it's just like, you have that small circle.
Yeah.
And then if that's multiplied by that small ds, you get a small fragment of that surface area. And when
There you go. So I'm actually going to back up a step here. I'm going to just say 2 pi r times ds, and we'll talk about the r. So I am revolving around the y-axis. I am using x as my independent variable. So if I were to basically, let's talk about just what's the radius going to be. Is the radius going to be something horizontal or something vertical? And hopefully you can see that the radius is going to be some horizontal measurement in this case. So I know it's going to involve x. And since I'm revolving around the y-axis and not some other vertical line, the radius is just simply going to be x. Because 2 pi radius is, this right here is circumference. So the integral of 2 pi times x ds, I'm going to go ahead and fill in a and b here. All right, tell me how to continue.
So then wouldn't you replace ds with the square root of 1 plus f prime squared
Mhm.
dx?
So yeah, this ds is absolutely tied to arc length. All right. Do I know what my limits of integration are going to be?
Be 1 and 0.
1 and 0. So go to 0 to 1. 2 pi x. Pretty easy function to take a derivative of. So derivative is negative 2x. Squared should be positive 4x squared. So I think that's a good integral. This one is not terribly complex. So let's go ahead and finish this one.
You can just take the inner one as like a u or something, and then it's
So I think, yeah, u equals 1 plus 4x squared, which means du is equal to 8x dx. Go ahead and translate the limit to the integral. So if x equals 1, u equals 5. If x equals 0, u equals 1. All right. So yeah, let's go ahead and start dropping things in here. Integral from 1 to 5 of, let's just do it in pieces, 2 pi x times
dx.
u to the 1/2 dx. All right, now we got to deal with got to finish getting rid of these x's.
X dx is du by 8.
Yeah, so that's another thing we'll do here. X dx equals du over 8. So I believe that's going to make this integral from 1 to 5 of pi over 4 u to the 1/2 du. And just to make this a little more digestible, I'm going to pull out that constant. All right, so this integral, we're going to get pi over 4 times 2/3 u to the 3/2, evaluated from 1 to 5. I know I kind of ripped through that at the end, but I believe it's right. Let me know if you see any problems or if you have any questions. All right, go ahead and move on. And really, those are the two big things from chapter 8. So I would still recommend going over the old homeworks and quizzes on that. It's been a little bit, I mean, we've done a lot of stuff with series and sequences since then, so it's definitely worthwhile to freshen those things up, I'm sure. All right, so into sequences now. I've given you the first several terms. And what I want to do first is this. I want to come up with a formula for this sequence. So how can we do that?
N over 2n plus 1.
N over 2n plus 1? Okay, let's give it a shot.
No. N over n squared plus 1.
Okay, so yeah, hopefully, yeah, I think 2n plus 1 might work for, I think it works with the first two terms, and then it stops. Actually, I don't even know if it works. I don't even know if it gets that far. So go ahead and leave that. I mean, this is sometimes going to be a process where you try a few things out. But really, we have n over n squared plus 1. Are we sure about that? And hopefully, and I really should put some more details behind this, because one thing I have noticed from the quizzes and stuff is just a little bit of carelessness with the indices. It really, you should make sure your starting index makes sense with the way you've defined your sequence. So where do I want n to start based on this?
One.
Should be 1. If you started at 0, your first term is going to be 1. Starting at n equals 1, hopefully you'll see that that's all going to line up. So yeah, I agree with this n over n squared plus 1. All right, if it exists, find the limit of the sequence. What is the limit of this sequence?
It'd be 0, right?
So so maybe, but how would we calculate that? So kind of walk me through this. So limit is n goes to infinity.
So because in the denominator has the highest n to the power,
Mhm.
its highest power, it's going to get the largest the quickest, which means it's going to approach 0.
Good. So yeah, and really, if you're trying to justify this, that's a totally fine way to say that a sequence is going to converge to 0. Maybe a little more concise is, I can divide all these terms by n squared, and I'm going to get 1 over n divided by 1 plus 1 over n squared, which now evaluating that limit gives me 0 over 1 plus 0, which is 0. So yeah, the limit of the sequence is 0. And finally, true or false, by the divergence theorem, that series converges.
May that be
think-
false?
Yeah.
I got to vote for false. Was that 2 votes for false?
Yeah.
Okay. Correct, it's false. So what does the divergence theorem actually tell you in this case?
It only tells you if it diverges.
Right.
That's all.
So the divergence theorem, like, it's I mean, if you have a sequence that does not converge to 0, then the divergence test basically ends the analysis for you. But the flip side of that coin is, if your sequence goes to 0, that it may still diverge. It does not mean it converges. So this tells us nothing when the limit of the sequence equals 0. All right, any questions here? No real example here, just kind of want to run through some of the theorems that we have here. So we're just looking at what theorems do we have for determining whether a sequence converges or diverges. I'll go ahead and get it started since we just talked about one, divergence theorem.
P series test.
P series. What else?
Geometric something.
Yep. So yeah, you can definitely test that condition for a geometric sequence or series. What else we have?
Alternating.
So remember, we're looking at just sequence here.
Oh, okay, sorry.
You're good. And I don't actually know if we ever talked about a P sequence. But the P sequence thing, the test works a little differently. If you're only looking at the sequence, then really I just need P to be positive. And I'll go ahead and underline sequence because to highlight that the P series does not have the same condition. What else? There are some other things we went over, maybe pretty early, but they're also very useful. So what about the squeeze theorem? And I think I called this one the limit continuity theorem. Basically, if you can find a function, basically, if you have a sequence that converges to something and you have a function that's continuous at that limit, then that basically the sequence built on that function is also going to be converged. And then the last theorem I remember that we should probably bring up is, if you have a sequence that has two properties at the same time, it converges. So if a sequence is blank and blank, it converges. So remember what those two things are.
Monotone and was it harmonic?
Not harmonic. So monotone. So that means it either, let's just say, increases. I mean, it really could be increases or decreases, but if it's monotone, it's always increasing, right? So what else do I need it to be? Because what else do I need it to be to converge? Because what if I have a sequence that graphs like this? Clearly monotone, but that is obviously not going to converge. So what other condition do I need?
Is
And
bounded?
bounded.
Bounded. Yep. So it needs to be monotone, and I need it to have Yeah, it needed to have a maximum value, or if it's decreasing, it needs to have a minimum value. So if its sequence is monotone and bounded, it converges. I don't remember what name I gave that, but I definitely know we talked about it. We definitely used it. And I think that's for sequences, not series, but for sequences, that's about what we have. So moving on. Let's find the sum of these series if possible. So that top one, can I find a sum of that series? What kind of series are these?
They're converging like to something, right?
Maybe. You can be a little more specific about that. Let's just look at the top one first. 27 plus 18 plus 12 plus 8. Do we think that's going to converge?
Yes.
Yes. How do we know?
I mean, my mind is thinking that's always getting divided by something or subtracting something.
Okay, so you said two different things there. It's always, I'm always dividing it by, so I'm always dividing one term by something, or I'm always subtracting by something. Is there some subtraction that I'm doing? I don't think you can say that. 27 minus 9 is 18. 18 minus 6 is 12. 12 minus 4 is 8. So I don't think we can set it up that way. But you also, is there something I'm dividing by to get from one term to the next? So let's rephrase that. Is there something I'm multiplying by? 27x equals 18. That means x is equal to 2/3. So I am multiplying by 2/3. Does that work between the next two terms?
Yeah, it works.
Okay. So what kind of series am I looking at then? So basically I can build this sequence out indefinitely by multiplying by the same number over and over again. What kind of series am I looking at here?
Geometry.
That's geometric, right? Does it have a sum?
Yeah.
How do I find it?
A by 1 minus r.
All right. What's A and what's R?
A is the starting value and R is the ratio.
So starting value is 27 over 1 minus 2/3, which should be equal to 81. All right, so that one has a sum. How about the bottom one there? Can we figure out if that converges or diverges?
That diverges
It diverges. How do you know?
because you split it up, and then you have -1/6. And then you have -2 raised to n. And then that's just increasing exponent.
Yeah, so yeah, let's go ahead and split it up like you said. 3 times -2 to the n times -2 to the -1. So that's -3/2 times -2 to the n, sorry. And if you write out a few of these, you're gonna get -3/2. Nope. Starting at n equals 1. Just be +3, right? Yeah, +3. And plus or -6 plus 12 minus 24. So yeah, so you're getting an alternating series that whose terms are getting further and further away from 0. Just diverges. Because common ratio is -2. Any questions on this one? All right, next one here. Evaluate the sum of these series. So let's talk about the top one first. Really, we should ask or figure out, do these converge or diverge before we go too much further?
The first one diverges.
How do you know the first one diverges?
P. Just this piece here. So.
Not exactly. So this is technically not a p-series. But how can I take advantage of a p-series to prove that this thing does diverge?
You can always approximate.
Approximation is not a proof though. So there is a way, there is a test I know that I can.
Would it be direct comparison?
Let's try direct comparison, but with what?
Would it be 1 over n?
Okay. 1 over n diverges. So what do I need to be true about 4n over n squared plus 2n?
The highest order is 1.
What do you mean the highest order is 1?
Sorry, it's it's -1, right?
I don't think I understand what you mean. What do you mean? What's -1 referring to?
It's like so 1 by n is like -1. So
Oh, the power is -1. Okay.
yeah. So that just means that if you add, multiply, everything else are just constants, like so constant with the diverging value, like that doesn't change anything.
I see what you're getting at. I still mean, what the question I'm really asking is this. So yeah, you're right that if we can compare with 1/n, we're good because 1/n diverges. So we can use it, but what we really need is an inequality. So which one of these do I need to be greater? 4n, the left or the right?
I believe the right.
So we know the one on the right converges, right? 1/n. So if the one on the right diverges and the one on the left is smaller, does that mean that the one on the left diverges as well?
Not necessarily.
Because think about this, what if I have 1/n to the 6th, which is, eventually is less than 1/n. We know 1/n is going to diverge and 1/n to the 6th is going to converge. So we actually need this. So we need this, but is this true? So let's make a string of inequalities here. Eventually we want this, greater than 1/n. Definitely can say this. This is greater than n/n² plus 2n. But what happens if I try to go one step further? Is this okay?
No.
No, that's not true. So I can't use direct comparison. But can I still use this harmonic series somehow?
Of course you can.
Okay. What other tests can I use?
Ratio test.
Actually, ratio tests will not really help here.
Oh yeah.
So I'll let you, if you want to convince yourself, and by trying it, you're going to get the limit of 1, which is kind of basically the only way that test doesn't help you. So direct comparison didn't work, but I can do a limit comparison test. Because remember, limit comparison, I'm just going to take the ratio, and I shouldn't use the word ratio to confuse it with the ratio test, but really, I'm finding this limit. The limit as n approaches infinity of 4n/n² plus 2n over 1/n. And if you don't see why this is the case, then go ahead and work it out on your own, but this limit is going to be 4. Which means since the 1/n diverges, then so does our other one that we really wanted to find out about. And just to put one more,
Professor?
go ahead, Rios.
Okay, so I was thinking about something. I'm not gonna take. Can I annotate this?
Okay, go ahead.
Just a minute. Yeah. So what I was sort of like thinking about was like that like you have sorry. Why is it not working? Just a minute. Yeah. What I was sort of like thinking about was like you have foreign by n over n plus 2. So I'm not going to take the nth term, but rather I'm going to take the 2 terms less. So that's going to be 4 over n minus 2 over n minus 2 over n minus 2 plus 2. And then you have this both getting canceled, and you have 4 over n. But this is
Oh,
still the
that's-
same. This
yeah.
is but this is still the same series, right? So that means it diverges.
Yeah,
Yes.
and that's really clever. The only thing that I would be careful about, if you do that, you're gonna have to be careful about where n starts. Because setting it up like that, you're opening yourself up to dividing by 0. So you would just have to basically make your starting value of n something that would avoid that.
Okay.
So I think the way you had it, n equals 2 is going to make that sequence break. You can divide by 0.
Mm.
That's a good approach though. So the limit comparison test. What am I looking for with the limit comparison test? What do I want to be true about the limit that I get in order to prove what I want?
Doesn't it have to be a whole number?
Doesn't have to be a whole number. It can be pi, and I still prove what I want.
Oh, isn't it like just a real number? That's what I meant. Like it's
Not
not
only
infinity.
real, but it has to be positive.
Okay.
So yeah, this greater than 0. Basically, if you get a limit of 0, and just to bring it back to this thing here, if you take that limit, you'll get either infinity or 0. The infinity is probably more obviously not useful, but the limit of 0, yeah, that doesn't tell you anything. Yeah, you definitely need a limit to be positive and real. All right, so no sum here. This diverges. So these probably look very similar. But one key difference. So 4 over n times n plus 2. Do we believe this converges or diverges?
Converges.
Converges. And rather than, I want the sum, we could probably also justify with a limit comparison, or maybe even direct comparison this time, that this converges. But what we should do, like, we want to find the sum. Do we know what kind of series this is? It might not be obvious just from looking at it. So let's break this thing apart with partial fractions. So if I use partial fractions, what's the decomposition going to look like? What's my first, basically what's like kind of like my skeleton that I'm going to use here?
It'd be a over n plus a over n plus 2, or b over n.
Yeah, right. Yeah, you're good. Yeah, that's good. So from here, we're going to get 4 equals a times n plus 2 plus b times n. What's a good strategic value of n to plug in?
-2.
-2 is good. From there, we get 4 equals -2b. So b equals -2. What's another good one?
0.
0. So that gives us 4 equals 2a. So that gives us a equals 2. And from there, we're looking at a new series, or not a new one, but a newly expressed one. A is, okay, 2 over n plus, or not plus, minus 2 over n plus 2. All right, from here, I'll let you all take over again. What should I do now to figure out what this series converges to?
It's still converges.
Yeah, it still converges, but I want to know the actual sum. Basically, what does it converge to? So do we remember, it's been a little bit now, but do you remember us talking about telescoping series?
You get all the chopped stuff, right? Like
All
you
the
have
what?
that, like you, it's just all those terms get canceled, like and then you have the last term and the first term.
So let's go ahead and look at a few of these. So I'll get 2 over 1 minus 2 over 3 plus 2 over 2 minus 2 over 4 plus 2 over 3 minus 2 over 5. And hopefully it's clear, or hopefully you're noticing something here. Now let's do one more. So hopefully you see that this and this cancel. This and this cancel. This and this cancel.
The way it's canceling is sort of I mean, is there a pattern? Like
Yeah, and let's go ahead and maybe do one more, and maybe we can notice what it is. So plus 2/6 minus 2/8. Did either one of those two new terms cancel anything?
only 2/6.
Yep. So that and that cancel. And really, hopefully you see that as I keep listing terms infinitely, what are the only terms that are gonna survive?
Only 2 and 1.
Yeah, so it's gonna be, you're gonna be left with 2 over 1 and 2 over 2. So this sum ends up being 2 plus 1, which is 3. Any questions on telescoping series? It's probably been a while since you looked at one, but that's why we're looking at them again.
I have a quick question on the first one we did.
Go ahead, Jacob.
So when finding something to limit comparison it to, like the
Yep.
1 over n.
Yep.
I always do like the highest power n in the numerator minus the highest power in the denominator to find that.
Yeah.
Like it did n is that how you're supposed to do it?
Yeah, I mean that's definitely a good approach, because you know what you're looking for is you're looking to get a positive limit. So let's say for whatever reason, say, or you know, I'm going to compare this with this 1 over square root of n. I know that 1 over square root of n diverges, so I'll go ahead and I'll try this. So that would give me 4n over n squared plus 2n over 1 over radical n, which simplifies to 4n to the 3/2 over n squared plus 2n. What is the limit of this thing that I made? So that limit is going to come out to that limit comes out to 0. So that's what you're trying to avoid. So really by comparing the highest power in the numerator to the highest power in the denominator, you are finding the correct. Basically, you're going to get a limit that is positive. But basically, if you don't go through that work to figure out, and really, a couple things to notice here. The more important one that I feel like we're kind of getting past, because it sounds like a lot of you are seeing that when you do a comparison test, you're almost always comparing with a p-series. So really, when you know that, you're just dialing in the value of p. You're trying to figure out what's a sensible value of p that'll give you a positive limit. And really, the only way to get that is by comparing those degrees, by comparing those powers. Because if you go, basically our n value or our p value here was 1, that ended up being a good comparison. If you go less than 1, you're going to get a limit of 0, which is useless. If you go higher than 1, you're going to get a value of a limit of infinity, which is also useless. So yeah, Jacob, long answer to your question was, yes, looking at comparing those powers is absolutely the way to go. All right, I have that we're just a bit past the halfway point. I have 7:44, so let's go ahead and take a bit of a break, and let's come back at 7:55. I'll see you all then. All right, let's go ahead and get back into it. All right, so now let's just analyze a few series without really. So, I mean, we kind of went over all these tests in different sections, but really I'm not going to, a big part of the battle with these is choosing what test to use. So how should I go after this series here?
I'm assuming a comparison test.
Okay. So a comparison test would be good. But which one? Want to try to limit or direct?
Limit. Limit.
Okay. Why are you choosing that one? Or do you just, is that just a preference or do you have another reason?
This is a preference.
Okay. So when you limit comparison, we need to compare it with some other series. So what's a good one to use?
1/n.
1/n. Okay, so let's try it. Just to remind you, the order I write this ratio in is totally arbitrary. You could easily do this as 1/n over the one I gave you. So from here, limit of n times n squared minus 1 over n cubed plus 1. All right, what does this limit equal to?
One.
Equal to 1. Yep.
So if this one was flipped, would it be, would you use the divergence theorem?
Oh, if the original sequence was the original one was flipped?
Yeah.
Yeah, in fact, let's just I'll play what if on that one. So you said use the divergence theorem. So the way to set that one up, I just want to look at the limit of not the series, but the sequence. What's this limit equal to?
It'd be infinity, right?
Yeah, so if you divide everything by n cubed, actually that's a little awkward. Let's divide everything by n squared. Yeah, and that goes to infinity. So yeah, from there I can just use divergence theorem with that one. The sequence doesn't converge to anything. So the series can't either. So yeah, this thanks. All right. We got a limit of 1. So what does that tell us?
It diverges.
So this limit is So this diverges. So the one that I care about diverges too. Okay, good. And right now there's lightning around me, so I'm hoping I don't lose power. If I do, we'll figure it out. Right, this one. So similar, but I made one change here. What do we know about this series?
It's alternating.
It's alternating. Are we allowed to use the alternating series test?
Yes.
Yes. So we're going to use alternating series test. What does that tell us?
Do we just need to, don't we just need to find the limit of n squared minus 1 over n cubed plus 1?
Yep. And I'm going to go ahead and shortcut this for us because we just looked at that. So that limit is 0. So what does that mean so far?
That it converges?
Can you be a little more specific?
Because I don't know, the limit is 0. So
Oh yeah, okay. So let me be more clear. Yeah, so it converges, but remember, we're dealing with an alternating series now. So it can converge in a couple of different ways. So really what I'm looking for is, does this converge conditionally? Or absolutely? So how do we figure that out?
Isn't it the absolute value of the series?
But the absolute value of the series this is just equal to this. Basically, all it's going to change, I'm going to take the alternation out of the series. But what does this series do?
Diverge.
Diverges. Yeah, we just looked at it. So it diverges. So what does that mean about our series overall? Does it converge absolutely or conditionally?
conditionally.
Converges conditionally. The alternating series converges, but the absolute value of it does not. Any questions there?
I have a question, alternating series in general.
Yep.
So I know it has to be decreasing. If it's
Mhm.
like 2n over 3n, that would still be decreasing, right?
Right, but let's say, so let's actually look at the one you mentioned. mean, if it was something like this, you really wouldn't need to get into anything as sophisticated as the alternating series test. What other technique could you use to draw a conclusion with that? So really the divergence test, the divergence theorem would give you that this diverges, because that sequence doesn't have a limit. So let's keep going. How about this one? How should we handle it?
Would it be the root test?
Why?
The
What tells you
root
the root test would be good?
Because the top and the bottom both are to the power of n.
And for this one, really I'll write it both ways, but the n through to the absolute value, which is the same as saying I think for this one, it might be more useful to look at this. Because if I express it like this, then how does this simplify? How does this simplify?
Is it n squared over 1 plus n cubed?
Yep. And what is this limit?
Would it be 0?
It'd be 0. So we got a limit of 0 from the root test. So what does that tell us?
Converges absolutely.
Converges absolutely. And just to be clear, for the root test to give that conclusion, what am I looking for in the limit? What has to be true about the limit?
It has to be less than 1.
Has to be less than 1. All right. Good. All right. Next one.
Would the integral test work?
Let's try the integral test. So what's the integral look like that I would like to set up?
It'd be x squared to times e to the negative x cubed.
Good. What are my limits on my integral?
1 and infinity.
Good. So looking at this integral. All right, so how do we find this integral?
Would you use u substitution?
Yeah, what's u equal to?
Negative x cubed.
And it follows from that du is equal to negative 3x squared dx, or x squared dx is equal to negative 1/3 du. All right, so let's start making some adjustments here. I am going to not worry about the definite integral. I'll just handle the handle it indefinitely first. So we have e to the u times negative 1/3 du I get, from there, I just get negative 1/3 e to the u. I'll just go ahead and in one shot do this. All right, so this limit then is equal to, so my limit is t goes to infinity of negative 1/3 e to the negative x cubed All right, I want the limit of this. What happens is t gets very large.
It gets really small.
The whole thing?
Just that part.
Yeah,
So it
just
goes to 1/3.
yeah, just the first term goes to 0. Second term is constant, so my limit is 1/3. What does that tell us about the series?
Does it converge to 1/3?
It does not converge to 1/3, but that actually is okay to. So yeah, we're not going to find the sum. But what is the fact that the integral converges? What does that tell us?
It also converges.
Yeah, it converges too. All right, good. All right. How about this one?
That's geometric, right?
Um,
Or it's close to, so we'd use the ratio test.
there you go. Yeah, so it definitely, I see what why you thought geometric, but technically the whole thing is not geometric, but the fact that that is there means that we should, yeah, if you see a series that has a geometric component to it, but is not totally geometric, ratio test is a good thing to look at. So want this limit. So we have n plus 1 squared plus 1 over 5 to the n plus 1 over n squared plus 1 over 5 to the n. So if I start canceling out what I can, I'll go ahead and expand the top there, get n squared plus 2n plus 1 plus 1. So n squared plus 2n plus 2. All times, actually, a lot of these things are going to cancel. All right. What is this limit?
1/5.
1/5. So what does that tell us?
Converges absolutely.
Converges absolutely. Because that is less than 1. Moving on.
The ratio test doesn't tell us the sum, right?
No, no.
Okay.
And there are, think about, so we've looked at lots of tests that tell you if there is a sum, whether a series diverges or converges. But really, there are very few instances where we can find the sum. In fact, I'll give you kind of a quick historical example here. We looked at this a while ago, probably when we did the integral test. This is exactly equal to pi squared over 6. You can look up the proof on why that is. It's very long. That was not a simple thing to solve. This limit. So if I were to ask you about that series, you could prove to me that it converges very quickly. It's very easy to justify that. We have no idea what this sum is. That's an open question. That's something that there's probably somebody working on it trying to figure it out, but right now we don't know what that is. So it's the moral of the story there. It's difficult to find these sums in most cases. All right, how about this series here? What if we expand this and do some rewrites? K to the 1/3 minus 1 over K to the 4/3 plus K. Does that give any kind of an idea where we might be able to go from here?
Would it be limit comparison?
Yeah, I think limit comparison is a good way to go. What's the series we should compare it with?
One over K.
1 over K. So we've done a couple of these things. I think the biggest thing to take away from this is that, yeah, limit comparison is probably the best way to go. I'll never promise it's the only way to go, but probably the easiest and quickest. Why is limit comparison a good choice here?
Because there's a K on the top and bottom.
Yeah, and really nothing else. Like I'll give you a quick counter example here. If we go back one, you know, we have this exponential term here, and those kind of things are, you know, they lend themselves really nicely to ratio tests, as opposed to things like, you know, really you just have, you know, your variable to multiple powers. Ratio test is not going to help you with things like that. If you need convincing, yeah, try the ratio test on that, and you'll see what happens. Yeah, limit comparison is, those comparison tests are really powerful. All right. How about this one?
Alternating.
Okay, alternating series tests. So, well, we know it's alternating. Now let's remind ourselves, what are the, so it's alternating, that's one condition. What are the other conditions that we need to look at to make sure we can use the alternating series test?
B of n's decreasing and positive, I believe.
Yeah. So let's break those up. Decreasing. I think it's pretty clear that it's positive. Is it decreasing? I think that's a little harder. I think that's not obvious that it may be decreasing, but it's not obvious. So I think we're going to need something else to make it clear that that's going to be decreasing. So keep in mind here, like focus on, you know, you have an exponential term, or geometric. What technique do those exponential terms lend themselves to?
Ratio test.
Yeah, I think ratio test is good here. So from here, look at the same limiters that we always do. And since it was brought up, the alternating series test, one thing I want to point out, what are the conclusions that the alternating series test can give you based on what the limit is? What are all the different possibilities that come out of it?
Like if it's converging.
Okay. How do you find out that it's converging? What are you looking for?
Oh no, it does not. It does not. Because I was thinking about that limit approaches 1 situation.
Yeah, so that's one of the conclusions, or one of the outcomes. If that limit is equal to 1, then what did you learn about the series?
It diverges.
If it's equal to 1, basically you get no info. It's not, you get no conclusion. So basically, if the ratio equals, that's not the right way to phrase this. So if the ratio is less than 1, what does that mean?
It converges.
Converges how?
Absolutely.
Absolutely. If the ratio is equal to 1, then you get no conclusion. If the ratio is greater than 1, what does that mean?
Divergent.
It's divergent. All right, so what's our limit then?
A 4th.
1/4. So that means we have learned that our series converges absolutely. Any questions on that one? I'm gonna go ahead and skip that one. All right, so on to power series. I want to find the radius and interval of convergence here.
Can we do the splitting up stuff here?
How would you split it up?
Oh no.
Yeah, I mean, when you have things that are added together, it's pretty easy to split them up. But let's say I wanted to do something like this, just arbitrarily. So it seems, at face value, like this would be true. But this is only true if both of these individual series converge. And right now, I don't know anything about how this series behaves or when it converges. So it can't really split it up that way. Breaking these things down, you know, we talked about our series and sequence laws a while ago, where basically, you know, among other things, the limit of the sum, basically, you know, there are a lot of them, but basically I'll just look at one of them. This limit is equal to but things like this are only true if both of these limits on the right actually exist. So we don't know anything about how we don't know if this thing converges at all. So we can't really break it apart because we might not know if it's true. So is there another way we can handle this? Think about the way we've usually dealt with power series and how to find where they converge for what x values they converge.
Ratio test.
Ratio test is good. So setting up the ratio test. So we have x to the n plus 1, or n to the 1, n plus 1 to the 4th, times 4 to the n plus 1. So, as usual, a lot of things cancel out. So I have n to the 4th times x over n plus 1 to the 4th times 4. Weird number. 4 times n to the 1, n plus 1 to the 4th. All right. Where should I go from here?
It's x by 4, right?
6 by 4?
X by 4.
Right. So yeah, the limit of, and I'll go ahead and just drop in some details here. Since my limit is only a function of n, and remember, this is ratio test. So I'm looking for where this converges. And like we just went over, the ratio test converges when this limit's equal to 1 or less than 1. Left out the 4. So because of that, I know this limit is equal to 1/4. So what I have is this: x times 1/4 is less than 1, or the absolute value of x is less than 4. So one thing I really wanted to hit today, because the quizzes pretty much all the quizzes I saw, maybe 1 or 2 exceptions, getting these ideas of the radius and the interval of conversions confused. So, you know, you need one to get the other, but they're not the same. So right now I have that the radius is equal to 4. And that comes directly from this: absolute value of x is less than 4. So that's the radius. That's as far as you need to go if all I'm asking for is the radius. Basically, you know, how many units can I be away from my center value? In this case, that's 4. So this is my radius of convergence. But now I want to find the interval. So I can translate this -4 less than x, which is less than 4. So here's what I know. Because of, you know, the way the radius conversion works, everything that's strictly within that radius of 4. So anything greater than -4 and less than 4, anything in that interval converges. And a lot, again, back to the most recent quiz, a lot of the things I saw were basically, all right, I wrote this down. That's my interval of convergence. Everything in there converges. And most people did not go any further. But what I really need to do to get the full interval of convergence is I need to look at the endpoints. So what happens when x is equal to -4 or when x is equal to 4? So from here, and now I just, yeah, I'm going to plug this value for x back into the original series. So I'm looking at the series from 1 to infinity of -4 to the n over n to the 4th times 4 to the n. -4 over 4 to the n over 4 to the n becomes -1 to the n over n to the 4th. What can you say about this series?
It converges.
Converges. Good. So because of that, I can modify my interval and put the equal sign, the less than or equal to sign, on the low end of this inequality. I know that when x is equal to -4, it converges. So now I need to see what happens when x is equal to 4. I get 4 to the n over n to the 4th times 4 to the n. Simplify as 2. 1 over n to the 4th. What does this one do?
Converges.
That also converges. So my interval really is the closed interval from -4 to 4. Everything in there, including the endpoints. Every x value on that interval will converge. So a couple things to look out for that I keep seeing a lot of. I saw a lot in the most recent quiz and probably the one before that, basically just writing down the interval convergence and not checking the endpoints. Or I saw a lot of people just including both endpoints without ever checking them. And in those cases, you might have looked at the notes I put on your submissions, and let's say that you had the answer right, but you didn't. Like, I didn't see anywhere where you actually tested anything. I can't give you credit for that. So remember, a lot of these things, the conclusions we're trying to get to is convergence or divergence. I need to see how you're justifying. It's not enough to show me that you're getting to the right conclusion. Any questions on any of that stuff? I know I threw a lot at you in terms of power series. All right. I don't think we have time to finish the rest of these, but we can get through a couple more. All right, so more about power series. I want to express this guy as a power series. So how can we do that? Remember the way that we first, no, go ahead.
A equals 5, R equals 4x squared.
What does R equal?
4x squared.
Good. So why Where's that coming from? How'd you figure that out?
Oh, it's just that for a geometric series, like when the summation for anything for a series where r is less than 1 is given by this a by 1 minus r.
Good. So yeah, geometric series that has this infinite sum of a over 1 minus r. So if you're able to realize that, yeah, there's definitely some parallels there. So if we can see this as a geometric sum, then, you know, we should be able to, you know, write out the first few terms in this series. Or if we try to represent this as a series, so we'll get, coming from Rios, we got the first term is 5. Common ratio is 4x squared, so 5 plus 20x squared plus 80 x to the 4th plus 320 x to the 6th, and so on. Can I write this as a power series now? Based on the first few terms that I've written out, can I generalize this for any value of n?
Would it be 20x to the 2n?
And really, I should have done this 0. If I plug in 0, I'm going to get 20. If I plug in 1, I am going to get 20x squared. If I plug in 2, I'm going to get 20x to the 4th. So I think the powers on x are okay, but I'm not really, nothing else is changing. So how can I modify this? Basically, all of my terms have a coefficient of 20. So oh, we said 2n. What modifications do we need to make sure that the coefficients actually change in the right way?
Um, 5 times 4 raised to n.
So let's try this one. If I plug in 0 for n, I'm going to get 5. If I plug in 1, I'm going to get 5 times 4 times x squared. That's good. N equals 2, I'm going to get 5 times 16 times x to the 4th. 5 times 16 is 80. I think this one's good. All right. Now, how can I find the radius of convergence?
Ratio test.
So we could do the ratio test. That would absolutely work. There is a quicker way to get the radius. And really, it comes from what we know about geometric series.
Anything less than 1.
Yeah, so what do we want to set less than 1?
X less than 1.
It's not going to be as simple as x.
Oh, x raised to n less than 1.
Not quite. So remember, geometric series, you know, this formula right here, this sum only exists if what is true.
Oh, 4 raised to n times x raised to 2n less than 1? Does that make sense? I don't know.
That's still probably a little bit too complicated. So back to the geometric series. What has to be true about R for a geometric series to converge?
That has to be less than 1.
So R less than 1. There's a little bit more to it, but we're on the right track.
Doesn't it have to be greater than -1?
Yep. So this is true here. So remember what our R is, 4x squared. So we need R to be less than 1. The common ratio for R series is 4x squared less than 1. So what does that mean about x? So because the R radius of convergence is 1/2. And you can probably see that, you know, any value of x that's less or between -1/2 and 1/2 is going to make the common ratio less than 1. So again, I think a lot of our, you know, our snap judgment is to see, all right, we're looking at a geometric series ratio test. Or if I wanted to raise convergence, that usually comes from the ratio test, and that would absolutely work here. It's just in this case, there's an easier way to get to it because we know how geometric series converge. Any questions here? All right. So how could I express this as a power series?
Take a derivative.
Take a derivative? All right. What is the derivative of natural log of 5 minus x?
1/5 minus x. Minus 1/5.
Yeah. So -1 over 5 minus x. So from here, what can I do?
You rewrite the derivative as power series, and you take interval.
Okay. So yeah, and hopefully you're seeing now again that this derivative, you know, is in this form, a over 1 minus r for a geometric sum. So it's almost there, it's not quite there. What else do we need to do to modify this?
Divide throughout by 5.
Right, good. So I'm gonna, yeah, basically factor out a 1 over 5. I have 1 over 1 minus 1/5 x. So from here, just like last time, now this is, yeah, we can now definitely look at this as a geometric sum, or infinite geometric sum. First term 1, common ratio 1/5 x. And now we can rewrite this f prime of x as let's start out by writing the first few terms in that sum. So 1 plus 1, actually I forgot we need this -1/5. 1 plus 1/5 x plus 1 over 25 x squared plus 1 over 125 x cubed, and one more. 1 over 625. To the fourth. All right, so now can we generalize this? I'm going to go ahead and leave out the negative 1 over 5.
One over 5n times x to the n.
Okay, let's test it out. N is 0, you get 1 over 1. That holds up. If x is 1, you get 1 over 5. Sorry, if n is 1, you get x over 5. X squared over 25, x cubed over 5 cubed, that's 125. I think this holds up. So this, remember, is f prime of x. So how do we get f of x?
You integrate, right?
Yep. So I'm going to go ahead and I'll just carry the constant. What's the antiderivative of this x to the n over 5 to the n?
X to the n plus 1 by 5 to the n plus 1, right?
So remember, when we integrate, what variable are we integrating with respect to?
And
No, it's actually not n, it's x. So remember these functions we're looking at, these are functions in x. So if we integrate, then we're really integrating with respect to x. So because of that, I agree with the x to the n plus 1. Really, we should divide that by n plus 1 as well. But the 5 to the n, as far as this integral is concerned, that 5 to the n is a constant.
Oh yeah.
Good. Yeah, and that's a really crucial distinction to make, and it's also unfortunately a very easy thing to miss. So now I'm going to go ahead and I'll incorporate that 1 over 5. And I believe that is a good representation. All right, and radius of convergence. What's our radius of convergence going to be this time?
Would it be 5?
Be 5 this time, because we know we want this to be true. Always want that to be true for your geometric series. So that is 1/5 x less than 1. Multiply both sides by 5, you get absolute value of x less than 5. All right, any questions here? So let's end here. Let's do this one, and then we'll go ahead and call it a night. There are, I think I put 22 examples on here. If you need to, you can go through and get some practice on these. I forgot to tell you all, I posted this set of slides on Canvas just before I ever marked on them. as soon as I log off here, or yeah, log off of Zoom, I'll put on the ones with all my annotations. But yeah, if you want to get the slide, it's on Canvas in that exam 2 prep area. All right, so we want Maclaurin series. So how should we start this thing? What do we need to do to get that series?
Find the Taylor series first.
Well, let's go ahead and what's the Maclaurin series? What does that mean?
So Taylor series centered at 0.
Right. So yeah, essentially what I'm asking for, we're going to find a Taylor series. So how do we start building a Taylor series?
Find the derivatives.
Good. So first derivative is going to be, need product rule, e to the x plus x, e to the x. And we want the first 4 non-zero terms. So, let's just kind of figure it out as we go. We don't want to take any more derivatives than we need to. But f of 0 equals 0. So we're not going to get a non-zero term from, the 0th derivative, the value of the function. But what's f prime of 0?
One.
That's 1. So there's 1. What about f double prime of x? Basically, we're probably going to see a pattern here if you don't already. F double prime of 0 is going to be 2. F triple prime is going to be e to the x plus e to the x plus e to the x plus x e to the x. Hopefully it's okay if I stop there. It seems pretty clear that the next 4 derivatives are going to give me these values. All right, so I have all those. That's definitely enough to get me 4 non-zero terms. But now how do I continue building this Maclaurin series?
X raised to n plus 1 by.
Yeah, so we're going to go 4th degree because we need to go to the 4th derivative. But yeah, just remind ourselves of what these things look like. The nth derivative at 0 divided by n factorial times x to the n. And really, we just need to kind of fill in the blanks here. But we have enough derivatives. We can definitely calculate n factorial. So our first term, I'll go ahead and write it in 0 just to show where everything comes from. But 0 times x to the 0 over 0 factorial plus 1 times x to the 1 over 1 factorial All right, so from there, start simplifying. Our first 4 terms are just x plus x squared plus 1/2 x cubed plus 1/6 x to the 4th. Any questions on how that got built? All right, let's go ahead and wrap that up. Hopefully you feel a little more comfortable with the stuff after looking at it again. So yeah, test is tomorrow night at 7:40. If you have any questions at all, and you don't feel like you don't feel like you want to wait until office hours are upon us, yeah, just send me an email, reach out to me on Slack or Canvas, and I'll definitely work with you. But I will go ahead and let you all go until tomorrow. Next quiz is online if you want to go take care of that, but remember it is not due until Thursday at 5 o'clock. If there's nothing else, I'll see you all tomorrow.
Professor, can we go over the whole I mean, I went through the Taylor, but the thing is like I was a little bit confused by that. Just one example to like get that under the wrap.